we're extremely interested in whether cycles, closed orbits, can exist in a system, and that's because they're one of the major fascinating features of a 2D system. And whatever application we're thinking about, we're really going to care whether it's possible for it to keep cycling on forever, or whether oscillations simply aren't possible. And so because this is such an important question, we actually have a number of methods that are oriented towards determining whether or not a particular dynamical system is able to have a closed orbit. And so I want us to look at a few of those methods. For example, if we had a system like this with a saddle point, just a single fixed point in the whole plane and it's a saddle point, we might ask, can a closed orbit exist, like the one that I just drew? And maybe we just want to appeal to index theory. And so if we go to index theory, when our only fixed point is a saddle, we know that every closed curve is going to either enclose no fixed points, in which case it has an index of 0, or it's going to enclose this saddle, in which case it has an index of -1. And we know that closed trajectories, according to index theory, need to always have an index of +1, and that the index is equal to the sum of the fixed points within. So we know that in this particular system, there simply can't be a closed orbit encircling this saddle point. And because we've said the saddle is the only closed orbit in the only fixed point in the whole system, we know this system can't have any closed orbits anywhere by index theory. So there's the potential that in some sort of simple cases, we'll be able to rule out some particular potential closed orbits using an index theory argument. The next really popular thing to do to attempt to rule out a closed orbit is to look for a function that decreases along trajectories. If we have a function that starts at some number, let's say 5, at this point on the trajectory, and it's decreasing as we go around the trajectory, so maybe now it's down to 0, -1, -2, -3, -4. Wait a second, when we get back here, we're back to where we started, where we knew that the function had a value of 5. However, we've also just determined it had a value of -4 because it was decreasing the whole time we went around, and so that would create a contradiction. So if we're able to find a function that decreases along every possible trajectory, then we would be able to show that none of the trajectories can possibly be closed orbits, since it's not possible to reconcile having a closed loop and having a function that decreases on the trajectory. And so this is some sort of almost like an analog to a conservative system. It's saying, no, instead of being conservative, this system is like losing energy along every single trajectory. And so we know we can never return to the same point because we know that the energy would have to be the same when we got there, but we've lost energy as we went along, and it's just not possible. The thing is, finding these types of functions can be quite difficult. So, as an example, say x dot is equal to the derivative of the negative of the derivative of some function with respect to x, and y dot is equal to the negative derivative of that with respect to v. So d dt of xy, this can actually be written as a gradient. And so we call this a gradient system. And now let's look at what happens to dv dt on a trajectory. So dv dt, as we travel a trajectory, is equal to dv dx x dot plus dv dy y dot. Just by the chain rule, v was a function of x and y, so we differentiate with respect to x, and then dx dt, plus is changed with y, dy dt. Oh, these should all be partial derivatives. Just a moment. Let's kind of overwrite with some nice partial derivative symbols. Okay, sorry about that. And now, let's look a little more closely at this. X dot, recall, was equal to negative of v sub x. So dv dt is equal to v sub x times negative v sub x plus v sub y, and y dot was negative v sub y. So this is equal to negative v sub x squared minus v sub y squared. Okay, and so this has been carefully constructed to always be less than 0. And so we see that dv dt is decreasing along the trajectory. And so if we were to integrate around a trajectory with dv dt, we're definitely going to get a number that's less than 0. But if we had a closed orbit, we would need v to return to what it had been. And so this is a problem. And so because this thing is always decreasing on trajectories, for a system of this type, which was a gradient system, there are just not going to be any closed orbits. So to rule out closed orbits, option 1 was index theory. Option 2, decreasing function. On trajectories. And so I gave this pretty simple example where the system was a gradient system, and if we looked at dv dt, the change in some particular function, we saw that it was less than 0, and so the function v was always decreasing on trajectories. And if we just construct a general function, somehow, miraculously, are able to come up with a function that happens to always be decreasing along trajectories for a system, we call that type of function a Lyapunov function, and it can allow us to show there are no closed orbits, but it's not very easy to find one. The only situation in which it's relatively easy is when that system happens to be a gradient system, and so then the function v is relatively obvious. Otherwise, I would say it takes some inspiration to find one. And then there's sort of a third option that, in sort of the same spirit as the Lyapunov function for ruling out closed trajectories, and that is we recall that it's possible to go from an integral about a closed loop in a vector field to an integral over an area via Green's theorem. So I'm going to recall Green's theorem for you, and basically, instead of showing that some function is decreasing along the trajectory, we need to show some kind of contradiction so that Green's theorem can allow us to conclude that there simply can't be any closed orbits. So if we use this theorem, so we're actually using, let's say that we have a vector function, and it's some scalar function times our vector field is the vector function. And so we take the integral of this, of dot n around this closed orbit. And I just want to point out to you that dot n is a normal vector this way, and that x dot is always tangent to the curve, and n is always normal to the curve. And so this case has been pretty carefully constructed so that actually this integral is equal to 0. So we've constructed this special case where we know that the line integral of this particular vector function about a closed curve would have to be 0. And then we use Green's theorem to say, wait a sec, we know it's equal to 0, but it's also equal to this area integral. And so if we're able to force this area integral to be non-zero, then that's a contradiction, and there can't be any closed loops. Because if there were a closed loop, this thing would be 0, but we're able to show that this thing is never 0, so contradiction. And so then that leaves us with the job of trying to construct some function g so that this divergence, the divergence of some scalar function g times x dot, is always positive or always negative. And so for simplicity, let's just say, okay, we're trying to find some g so that this thing is always negative. This is called Dulac's criterion. And it allows us to rule out a closed orbit, just like the Lyapunov function did or index theory did. But again, it's not so easy to use because it's not at all obvious how to find a function g. So the upshot of this method is that we need to construct some g so that this divergence is less than 0 everywhere in a region of interest, and then we can use this argument via Green's theorem to argue that there can be no closed orbits in that region. And there's an example of this in the book, but it's really not clear how to construct these functions g, and I would guess that it just takes a ton of trial and error. So that was option 3. Option 3, Dulac's. Okay, and so we have 3 basic options for attempting to rule out some kind of closed orbit, some kind of periodic orbit existing in our phase space. And the next thing we'll look at is whether there are any ways to argue that a closed orbit must exist in some region of the phase space.